Hey guys, so for this video we're going to be looking at force diagrams and unbalanced forces or net forces. I'm looking at the particle model, net force particle model worksheet 1 and worksheet 2. So let's get started. An elevator is moving up at a constant velocity of 2.5 meters per second. The passenger has a mass of 85 kilograms. The constant velocity tells me that my forces are balanced. I'm going to have a normal force on the person and a force of gravity on the person. Part B, it says calculate the force the floor exerts on the passenger. So I know that this normal force is on the passenger by the floor. So part B is asking me to find the normal force. Since I know my force is equal to the force of gravity, I'm just going to take the mass, multiply that by 9.8. and I want to get 833 newtons. So my normal force must also be 833 newtons. Okay, so for number 2, it says the elevator now accelerates up. Construct a force diagram for the passenger. Since we have an upward acceleration, my motion map would look something like this. The velocity vectors are going to get larger, so that means my acceleration vectors are going to go in the same direction. So when I look at my force diagram, I'm going to have a normal force and the force of gravity. Now the normal force needs to be larger than our force of gravity in this case. The force of gravity has not changed because I'm still talking about the same person, so I'm going to put 833 newtons there. Part B, write an equation for the vertical forces on the passenger. So since these forces are not balanced, we are writing a net force equation in that vertical direction, and that's going to be the normal force minus 833, because I want to treat up as positive. That is my sign convention. And that equals mass times acceleration. Part C, calculate the force the floor exerts on the passenger. Again, this is asking me for my normal force. So I want to say N minus 833 equals the mass of the person, 85, times our upward acceleration of positive 2 meters per second per second. So when I do 85 times 2, I get 170, add 833 to both sides, and I want to get N equals 1,003 newtons. Number 3, upon reaching the top of the building, the elevator accelerates downward at 3 meters per second per second. So upon reaching the top, so here we're slowing down. My motion map is going to look like this, so my acceleration needs to go in the opposite direction. So when I go deal with this 3 meters per second, I need to make sure I stay with my sign convention that up is positive, and I'm going to record my acceleration as negative. Now for the force diagram, my net force, or the larger force, needs to be in the direction of my acceleration, so that means the force of gravity must be larger than my normal force. Write an equation for the vertical forces. Again, since these are not balanced, we're looking for the net force in the y direction. I'm going to keep the same sign convention that up is positive, and I'm going to say N plus a negative Fg, or N minus Fg, equals mass times acceleration. Part C, calculate the force the floor exerts on the passenger. Again, that is asking for the normal force. So N minus 833, we're still talking about the same person, equals 85 times a negative 3 now, because my acceleration needs to be negative based on my sign convention. So I'm going to do 85 times negative 3 plus 833. And I get a normal force of 578. Just a simple check. This needs to be less than my force of gravity of 833, so that makes sense. Again, when you're dealing with an elevator problem, the way you perceive your weight is the normal force. So if you feel lighter, then that means the floor actually is not pushing up on you the same amount that it usually does. So your normal force is smaller in that case. Number 4. While descending in the elevator, the cable breaks. How big is the force on the passenger by the floor? In this case, imagine we have the person now and the elevator, they are both falling and they are both going to fall with the same acceleration of negative 9.8. So since they're both in free fall, the elevator and the person are falling together, and there's no upward force that this elevator is going to apply to the person, so 0 newtons. Number 5, a 70-kilogram skydiver jumps out of an airplane. Immediately after jumping, how large is the skydiver's acceleration? So as soon as she jumps out of the plane, he is going to have an acceleration of negative 9.8 meters per second, given again that I stick with the convention that up is positive. Her velocity is going to increase, and the acceleration at the very beginning will be negative 9.8. Now, that's because immediately after she jumps out, enough time has not elapsed for air resistance to play a role. So actually our acceleration will decrease until we reach a constant speed, and that's called terminal velocity. But the force diagram, immediately when she jumps out, is just the force of gravity. It's not until later when we see that we have force of gravity and a substantial amount of drag force. Part B, upon reaching a downward velocity of 100 miles per hour, 300 newtons of drag resist the diver's motion. Draw a force diagram. So we have a force of gravity here, which is going to be equal to 80 times, not 80, 70, because that's my mass, times 9.8. And we're going to have 300 newtons of drag here. How large is the skydiver's acceleration? So I want to continue with the sign convention that up is positive. I want to say 300 minus, not 80, 70 times 9.8 equals our net force, which is mass times acceleration. Okay, so 300 is the drag, minus 686 equals 70 times A. When I solve this, I get negative 386 equals 70A. Divide 386 by 70. And I get an acceleration of negative 5.5 meters per second. That does make sense for my sign convention because I should get a negative acceleration. Alright, number 6. Draw a force diagram for a 900 kilogram car that exerts 5,000 newtons of traction force on a level road while being opposed by 1,000 newtons of friction. Now the important thing here is that we just understand we have two forces in the horizontal direction that are opposing each other. This traction, although we don't really understand that word completely, that is the force that allows the car to go forward. So you have to think the car's tires push back on the ground, so the ground pushes forward on the car's tires. It's that idea with traction. So here we have the traction of 5,000 newtons. Here we have 1,000 newtons of friction and drag combined. It's going to have a normal force and a force of gravity that I know are balanced with each other. Now, write a net force equation for the car. So first of all, our net force in the y direction is 0. Those forces are balanced. The net force in the x direction, however, is going to be 5,000 minus 1,000, and that equals mass times acceleration. Now it says calculate the acceleration of the car. We know we're accelerating in the horizontal direction. So I just need to do 4,000 equals 900 times the acceleration. So my acceleration is going to be 4,000 divided by 900, and I get 4.4 meters per second. Alright, number 7 was a system, and we did this one in class, but I'll go ahead and go over it quickly. If we just look at the forces here, there's going to be a tension, and those two tensions are equal and opposite to each other because of Newton's second law. And there's a force of gravity on here. Here's a force of gravity, and here is twice that force of gravity. I'm going to call this mg. This will be mg, and this force will be equal to 2mg. And then, of course, there's tension and tension here that's equal and opposite. Now these tensions in each one, so like this tension may not be equal to that tension because they're all going to have different accelerations, but for the system itself, those are balanced. And then of course there are tensions. There is a tension here and here, but I'm not worried about that. Again, it's a Newton's third law pair, internal force. There's no friction on any of these systems, so I don't need to worry about that. It says which system has the greatest net force. So net force being the only force that isn't balanced. Here we look, our net force is the force of gravity, which is mg. This is mg, this is 2 mg. So it looks like system C has the greatest net force. Now, which system has the least inertia? Inertia is directly dependent upon the mass of the system. So the one with the smallest mass is going to have the least amount of inertia. That means it's going to be the easiest to get going, and it's also going to be the easiest to stop once it's accelerating. So system A, because it has the least amount of mass. Now determine the acceleration of each system. So acceleration, Newton's second law says, is net force divided by the mass. So we're going to have the acceleration of A be the net force of A, which is mg, over the system mass. Now since there are two masses here, I'm going to put 2m. So it looks like my acceleration is half of g. The acceleration for B is going to be equal to the net force on B, which is mg again, and its mass is 3 mg. The masses cancel. Ooh, not g, sorry, just 3m. The masses cancel, so it looks like the acceleration for B is 1/3 that of g. And we know g is that 9.8 meters per second, represents the acceleration due to gravity. Finally, if I'm looking at the acceleration for system C, the net force is 2 mg and the total mass is 3m. So it looks like this acceleration is going to be 2/3 of 9.8, or 2/3 of g. Okay, here for number 8 it says draw a quantitative free body diagram. So I'm going to start by tilting my axis. Now I'm going to have a force of gravity. Since it's 30 kilograms, my force of gravity is going to be 294 newtons. If this angle is 55, that means that this angle is 55 degrees. So my FGX is going to equal 294 times the sine of 55 degrees. And that equals 241 newtons. My FGY is going to equal 294 times the cosine of 55, or 169 newtons. My normal force then is also going to be balanced with FGY, so this is going to be 169 newtons. And finally, it tells me I have a force of friction here, which is 160 newtons. So there's my quantitative free body diagram. Part B says write an equation for the forces on the child parallel to the slide. So our net force equals 169, this FGX, minus the force of friction, which is 160, and that's going to be equal to mass times the acceleration. So we have 9 newtons of unbalanced force equals 30 times our acceleration. When I divide by 30, I get an acceleration of 0.3 meters per second, and that is assuming that this general direction is positive. This was part C. Alright, so here we are looking at just word problems. So we have some helicopters accelerating up, so we must be speeding up, which tells me my acceleration is going to be positive. My sign convention will be that up is positive. So I'm going to have the force of gravity on this helicopter, and I'm going to have a lift force. Okay, this is just air getting up under the propellers to lift it up. The force of gravity is calculated by doing 4,600 times 9.8. It says determine the lift force. So to do that, I use Newton's second law. The lift force, which I'm going to call FL, minus my force of gravity is going to equal mass times acceleration. So FL minus 4,600 times 9.8 equals 4,600 times A. So to do this, I'm going to just 46, well, my acceleration is 2, I need to plug that in. So 4,600 times 2 plus 4,600 times 9.8. You should get a lift force equal to 54,280 newtons. And it makes sense, it definitely should be larger than my force of gravity. Now for number 2, it says the maximum force that a grocery bag can withstand is 250. So that's just a general statement. Now it's saying suppose that. So now we're going to deal with what's actually going on. We have the bag filled with 20 kilograms of groceries lifted with an acceleration, so I want to say that's a positive acceleration, of 5 meters per second. Do the groceries stay in the bag? So first of all, when it has a positive acceleration, the upward force needs to be larger, and that would be like the tension in the bag. You can call it F pull, whatever you want there. Force of gravity is going to be 20 times 9.8, which is 196 newtons. And so I need to figure out, if I'm pulling it up with this acceleration, what is the force of my pull, or the tension in that bag. So I want to say T minus 196 equals the mass of the groceries times my acceleration. So obviously that's going to be 296 newtons, and 296 is greater than that maximum 250 that I can withstand. So do the groceries stay in the bag? No, the bag rips. Okay, a student standing on a scale in an elevator at rest sees that his weight is 840. Now this weight is never going to change. As the elevator rises, the scale reading increases. So we have a rise here, and then returns to normal. When the elevator slows to a stop at the 10th floor, the scale reading drops, then returns to normal. Draw a motion map for the student during his elevator ride. So we know when he's going up, he is actually accelerating, so the velocity for some period of time is getting bigger, and I want to stick with my sign convention that up is positive, so I have a positive acceleration here. That means my upward force must be larger than my force of gravity, so I have 840 newtons here and 1050 newtons here. Now when I come to a stop at the top, my motion map looks something like this. Now I'm moving with some constant speed. My velocity vectors actually get smaller because I'm slowing down, so my acceleration at that moment should be negative, assuming I'm still dealing with my up is positive sign convention. So in this case, my upward force needs to be smaller than my force of gravity, so that's 840, and this is going to be 588 newtons. Determine the acceleration at the beginning and at the end. So for the acceleration here, I'm looking at net force over mass. My net force is going to be 1050 minus 840 over the mass. I need to find my mass by doing 840 divided by 9.8. So I get about 86 kilograms. I'm just going to round it for the sake of time. So 1050 minus 840 divided by 86 gives me acceleration of positive 2.4 meters per second. And then down here, my net force is the same, or my acceleration is calculated the same way. My net force, which now is 588 minus 840 over the same mass of 86. So my acceleration is going to be 588 minus 840 divided by 86. Oh, goodness. Negative 2.9 meters per second. All right, number 4. We have another elevator problem. So a sign on an elevator says that the maximum occupancy is 20 people. Suppose that the safety engineers assume an average rider is 75 kilograms. The elevator itself has a mass of this. The cable supporting the elevator can tolerate 30,000 newtons. What is the greatest acceleration the elevator's motor can produce without snapping the cable? So really we want to use the max tension here. I'm looking for a maximum acceleration. So I want to fill the elevator with as many people as it is rated for. So I want to say we have the mass of the elevator, which is 500 kilograms. And then we have 75 kilograms times 20 people. Okay, so kilograms per person, and we have 20 people. So to get the mass of the total people, I'm just going to do 75 times 20. I get 1,500 kilograms. So this total mass together is going to be about 2,000 kilograms. So now to find that maximum force of gravity, 2,000 times 9.8 is going to equal 19,600 newtons. So to find my acceleration, it's again net force over mass. So 30,000 minus 19,600 over my total mass of 2,000. You get an acceleration of 35.2 meters per second. Alright, that's everything for worksheets 1 and 2. Hope that was helpful. Let me know if you have any questions.